Okay, so this will be part of chapter 5 of our syllabus. Chapter 5 is about frequency response, and we will be talking about series resonance, parallel resonance, and some basic filter concepts. And also, if we have time, we can also discuss some harmonics. So now, in the previous chapters of our discussions, when we are plotting uh, current or voltage, what we are doing is we're just plotting them into the time domain. So, for example, if you have a sinusoidal system, and this is the graph of the sinusoidal, this one is called the time response. Or in transient, we also discussed that in circuits 1. When we say time response, this is the response of your voltage or current or anything, but it should be with respect to time. Now, here in this chapter, we will change that. We will be talking about frequency response. So if we say it's a frequency response, instead of plotting this in with respect to time, we will be plotting the voltage and the current with respect to the frequency. That's why it's called the frequency response, or simply omega, where omega is, you already know what's omega. Omega is the angular frequency, which is equal to 2 pi of the frequency. So we will plot the voltage, current, what happened to the voltage and the current when we change the frequency. Because we will be talking about sinusoidal system, because we're talking about frequency. And in DC, we don't have frequency. So here, in this chapter, we will be talking pure AC system. So in frequency response, to draw the frequency response, let's try to consider first a series RLC. So let me draw a series RLC here. So we have R, we have L, and we have a capacitor. This is an RLC system, basic RLC circuit, R, L, and C. So here we have a voltage, let's call it V, and the result is we have a current I. So when we plot the frequency, we look at the characteristic of these three different parameters. For R, it's just a pure resistance. Resistance is just a resistance. It does not change with respect to time or the frequency. The other parameters are the reactances of the inductor and the capacitor. So here we have XL, here we have XC. And these reactances, these two changes with respect to frequency. Because if you remember the formula for the reactances, for XL, the formula is just equal to omega times the inductance. While for XC, this is 1 over omega C. And omega is, we know, that's 2 pi F. So if we change the frequency, so what happens to XL? What happens to XC? So if we plot this, let's look at the current. Let's plot this with respect to the current. So if this is the current, I, this is our frequency, omega. When we are in low frequency, so meaning the frequency is small, so what happens to the value of XL when the frequency is small? When XL is approaching 0, or when omega is approaching 0, XL is also approaching 0. While for this one, when omega is approaching 0, what happens to our XC? When this approaches 0, and you take the limit of that, then our XC approaches infinity. So what does it mean when our XC approaches infinity? This is a reactance. It's equivalent to resistance. So if that happens, then it's a very large quantity. So remember, our current is equal to the voltage all over Z, where Z is equal to the square root of r squared plus x squared. This x is the difference of xl and xc. So if you make this xc larger, or if you take this as xc, if you make that larger, so what happens to the current? So the current, this term here in the denominator will also increase because x is increasing. You square that, you add it with something, it's still infinity. And a number divided by infinity then will result to the current will also approaches zero. So the lower the frequency, the lower the current. So it's somewhere here. It can be zero or somewhere in that part. Then if we increase the value of our frequency, so what will happen if we try to increase omega? So approaching this time, instead of zero, omega is approaching infinity. And then what will happen with our XL when omega approaches infinity? Because this is just omega times L, and this also approaches infinity. While for the XC, it's the other way around. So this one, when omega approaches infinity, our XC is approaching zero. Because when you divide a number with infinity, that's just equal to zero. But still we have an infinity here. So this means the inductance is an open circuit when the frequency is approaching infinity. So these are the characteristics of inductors and capacitors. When the frequency approaches infinity, the inductor acts like an open circuit. While for the capacitor, when the frequency is low or zero, then the capacitor acts like an open circuit. So somewhere here, if it's high frequency, so our current is also zero. But what happens when the frequency, the proper frequency, when we take XL, becomes exactly equal to our XC. So if that happens, then it can be located somewhere here. Let's say this is the frequency of that. Then our current, because again, I is equal to V over Z, and Z is equal to R plus J XL minus XC, right? So if XL is equal to XC, this term is equal to zero. So if this term is equal to zero, then therefore that is the time that our Z is minimum. Z is minimum. Z is minimum when XL is equal to zero, and that's just equal to R. That's the minimum impedance that we will be getting in the circuit RLC. Then if it's the minimum impedance, because this is current is voltage over that Z. The higher the impedance, the lower the current. The lower the current or the impedance, the higher the current. So if this is the minimum value for impedance, then the current that we will be taking will also result to the maximum current, because that's the lowest value for Z. And that value will be somewhere here. It will look like this one. And this is, if this is our maximum current, IM here. IM when Z is equal to Z minimum. Somewhere here. And that frequency here that will make the current the maximum is this frequency that make the reactive, inductive, and capacitive reactance equal. And we call that, this is what we call the resonance frequency. Resonant frequency. You can call it omega R. So that's the resonance. When we say resonance, so this is the frequency response. This is what we call the frequency response. Frequency response. And resonance is defined as this is a phenomenon when XL is exactly equal to XC. When the inductive reactance become equal to the capacitive reactance. That phenomenon is called the resonance. And the frequency that make it equal, we call that the frequency, resonant frequency. Omega R is the natural frequency, resonant frequency, natural resonant frequency, resonant frequency, and FR is just equal to the resonant frequency. So the condition is when we say resonance, XL should be equal to XC. Now, what will be that value? How can we calculate that value? So that's the next thing that we'll be doing. By using this condition where XL is equal to XC, we can derive the formula for that natural frequency when we try to solve the resonance frequency. So we know that XL should be equal to XC. This is the condition. Why? Because it's the definition of resonance. And then, what is XL? XL is omega times L. And this omega here, because they are equal, this should be the resonant frequency. And for XC, this is 1 over, again, it should be omega R times C. And if I try to solve for omega, omega R squared is equal to 1 over L times C. And simply omega R, or the resonant frequency, is equal to 1 over the square root of LC. So if you want to solve for the resonant frequency, this is the natural resonant frequency. So if you want the actual frequency F, and call it FR. Some books name it FO. This will be equal to 1 over 2 pi LC, because omega is equal to 2 pi times F. And the main application of this resonant frequency is in communications, or in wireless communications, or power. It can also be used in wireless power transmission. And we transmit power through what we call the channels, and these channels are these frequencies. So when we try to tune in a frequency, in a specific frequency, for example, this one, omega R, then there are some parameters that we want to look at. So if we draw again that plot here, let's say this is our frequency response for an RLC circuit. Now, there are factors that describe this response that we want to consider when we are designing circuits. And what are those factors? The selectivity of that circuit. When we try to select the frequency that we want, and how fast and how can we select the proper or the right frequency, it depends on this frequency response. So if it look like this, then if you observe, if you can describe or differentiate the value at the maximum and at this part of the response, the difference between the currents is just very, very small. You cannot really exactly say that they are maximum if you are in this part. So therefore, it means the selectivity of your circuit is poor. So to increase that, what we want is we try to sharpen our curve into like this one. So this means the selectivity of this one is better. Selectivity is better than this one. Better than this, or the white one, this curve. So the selectivity of the red curve is better than the selectivity of this white here. And to describe that selectivity, we have two factors to quantify those selectivity. And the factors are, the first one, we call it the quality factor. Quality factor. And the other one is the bandwidth. Bandwidth. So first, let's talk about quality factor. So what is a quality factor of a certain circuit, of a resonant circuit? Quality factor. So we define this one, or we can just simply write Q factor, or simply Q. Some books just only use Q. Q is defined as the equal to 2 pi times the peak energy. Peak energy, this is the sharpness of the curve. Peak energy stored in the circuit. Stored in the circuit all over the energy dissipated. Energy dissipated by the circuit, by the circuit. This is for uh, in one period, in one period of resonance, of resonance. So this is the definition, basic definition of a quality factor. And if we solve the actual formula for this one, quality factor based from that definition. So this will be equal to 2 pi times the peak energy. The peak energy will be the energy that is being stored in the inductor. And if you want to try to solve the energy stored in the inductor, that's just equal to 1/2 L times I squared. All over the energy being dissipated. The energy being dissipated while in one period is just 1/2. This is 1/2 of I squared, or this is half power, but we still need to multiply because this is one period of frequency, so we need to multiply it by 1 over f of r. Then simplifying this, we can cancel out I squared. We have 2 pi here, and we have fr. We can put it in the numerator, so Q factor now. Q factor will be equal to 2 pi times this fr here. And we have L, so we multiply it with L. 1/2 will cancel out. Then I squared will also cancel out. We only have R at the denominator. And what is 2 pi f of r? That's actually our natural frequency omega r. So we can say that Q factor in terms of omega r will be equal to omega r L all over r. So this is another definition for a Q factor. You look at the numerator. Numerator is actually just the XL, the reactive inductive reactance all over the resistance. It's just the ratio of the reactive inductive reactance versus the the resistance R. And we can also do that with respect to the capacitor instead of the inductor. And this will become XC. And what will be the formula for XC? XC will be 1 over omega times C. So the formula will become Q factor can become, in terms of the capacitor, omega R times C. So that's our XC. Then you divide it with R, or just multiply here with R. This is another formula for the Q factor. And the other parameter that describes the selectivity of our frequency response is what we call the bandwidth. And the bandwidth is actually here. It's if you have the current at half frequency or half power. So this is the current at half power, and that's just equal to I maximum divided by square root of 2. The frequency here, the equivalent frequency here and here, so there are two frequencies. We can call this one the lower frequency, omega L, or omega L, and this one is the upper frequency, omega U. The bandwidth is just the difference. This is the bandwidth, the difference between the two. This length is the bandwidth. So this is the bandwidth. So the formula for bandwidth, BW is just equal to omega, the upper omega, minus the lower omega, omega here. And if you want to solve for this omega, the actual, in terms of R, C, and L, omega, the lower omega is the omega at this point, and upper omega is the omega at this point. So if you want to solve that, you'll be using the condition that the current here is equal to that one, Im over square root of 2. Or we can also use the voltage. So if the voltage at half power frequency, you call it half power frequency, is also equal to B maximum divided by square root of 2. So the power, because this is half power frequency, this is just 1/2 I squared times R. That's the average power dissipated by the RLC circuit. Then how about the highest power? The highest power occurs when we are in resonance, P omega naught, and this is also we can also use the voltage. So 1/2 the voltage squared, maximum voltage, divided by the resistance R. And at certain frequencies, when omega is equal to, instead of omega naught or omega R, this is omega R. When omega is equal to omega, the lower frequency, omega L, what will be the power? So the power will be the same as the power when omega is equal to omega U, or the upper omega. Let's just change this. Omega is equal to omega U. Why? Because they have the same here. If you look at this omega L, the same current. If they have the same current, then they have the same. They also have the same voltage. Then they have the same power, because they are half power frequency. They call it half power frequencies, omega L and omega U. Omega L and omega U, these are called half power frequencies. These are the limits of the bandwidth, the upper part and the lower, omega U and omega L. And if that is the case, what will be the power? So what will be the power? Because for here, let's use this formula. So P omega L. So we just need to change this Bm squared here. Instead of the maximum voltage, we will be using the actual. Here, we divide it by square root of 2. So this will become, so 1/2, or Vm is Vm over square root of 2. You square that, this part here, then we have 2 times R, 2 times R. So for omega R, this is just maximum. But we are in omega L, then the value will be divided by square root of 2. Should be divided by square root of 2. Now, we continue the solution. So what will be the power then? So this will be equal to what? This will cancel out because this is squared and this is 2. So the answer will be just simply Bm squared all over or they will not cancel out because they will multiply each other. The square root and the square will cancel out. This will be 2 times 2, and that's 4 times R. So this is the power at the lower part of the frequency. And for the other one, for omega U, that's also the same thing. Why? Because they have the same value for the voltage. It's also Vm over square root of 2. So this is the power during the half power frequencies. Then the half power frequencies are obtained by setting our Z equal to the square root of 2 times R. So what is our impedance? Remember the formula for the impedance. This is R squared plus, we have our reactances, omega L. So I just removed the J because we have a square root here. Omega L minus 1 over omega C. This is XL minus XC squared. That's the magnitude of the impedance. And we just need to equate this to square root of 2 times R. And we can now solve for our omega L and omega U by solving the omega here. So because this is quadratic, there will be 2 values for our omega. So we can do that. So R squared equals, we square both sides, R squared plus omega L squared minus 2 times omega L times this one. So that will be equal to just L times 1 over C, and we have 1 over omega C squared. And this is equal to square root of 2 times R. Then, so there are 2 values. Omega L squared minus 2L over C minus 1 over omega C squared is equal to the square root of 2 times R minus R squared. Or this should be, I forgot to put the square root. If you continue to solve this one, you can just put the values for omega 1 to minimize the time for this video. Omega L will be just equal to, because this is negative, because this is the lower part of the frequency. This is much lesser than, it's much lesser than the resonant, and also the upper cut-off frequency. So there should be negative R over 2L, then plus the square root of R over 2L squared plus 1 over LC. And for the upper part, upper cut-off frequency, we can make this one, we add this to the the frequency on the resonant frequency L over 2L, then plus the square root of R over 2L squared plus 1 over L times C. And some of the book, they substitute this voltage, they make this one omega alpha, and this one is omega R, because one omega R squared, alpha squared, and this is also alpha R over 2L. Then we need this because these are the, remember, these are the upper cutoff frequency and the lower cutoff frequency. We also call them the half power frequencies. Then if you want to solve for the bandwidth in terms of the natural frequency rather than that just a simple frequency f, this will be equal to omega u minus omega l. So if you subtract this, the bandwidth now will be just equal to 2 all over L. So because this is 2 and 2, so R 4 over L, 1/2 plus 1/2. This will cancel out. So the bandwidth, formula for the bandwidth in terms of the natural frequency is R over L. But if you want to make it in terms of the frequency, the actual frequency, you can just multiply it by here. You can multiply it by 2 or divide it by 2 pi, so that it will be a frequency. So we can write this R over 2 pi L. R over 2 pi L, because RL is just equal to the bandwidth with respect to the natural frequency. And if we relate these two, the Q factor and the bandwidth, we have a relationship between the two. So remember, Q factor is just equal to omega R times L all over R. So here, if we multiply this one, if we try to multiply L with omega R at the denominator, and we just inverse that, and that will become omega R times L all over R, which is just the Q factor, omega R L all over R. So let's try that. So if I divide that with the bandwidth, I divide it with the frequency, resonant frequency, and if I input it here, this will become R all over 2 pi FR times L. Then if we look at the formula for Q is equal to omega R times L, but omega R is just equal to 2 pi FR also. So 2 pi FR all over L. So if you inverse that, that will be equal to this. So this is just equal to 1 over the Q factor. So the relationship between the two, if I solve for the bandwidth in terms of the Q factor, and that's just equal to F of R all over the Q factor. And if I want to solve for the Q factor in terms of the bandwidth, then I just need to multiply it with F of R, or F of R all over the bandwidth, and bandwidth in terms of the frequency here. So this will be F upper minus F the lower cutoff frequency. So this is the relationship between the two parameters. So this is series resonance. This is only for the series resonance, and for the parallel, we will talk about that in the next video.